to look at the different types of images formed by a convex lens, and we're going to summarize them in our table on the right hand side. So let's get started. I'm using the ophysics.com simulation for this. It's a really good, accurate one, and I'll include a link to this where possible so you can try it for yourself. So let's get going. What have we got here? We've got on the left hand side an object, you can see that clearly marked, and on the right hand side it's image. And what we hopefully know before coming into this is the fact that depending on the position of the object we will get different types of images, and that's what we're looking at here. We should note a few things down about our image, our lens, sorry. Firstly, we've got a focal length of 4, okay, and that means that our focus is located 4 away from the center of the lens. We've got one on the right and one on the left, and they're important for drawing our ray diagrams, as you can see. In this situation, we're at a distance d0, which is greater than 2f. So f being 4, 2f is 8. We're at a distance greater than 8 away, and that's 8 boxes. It doesn't really matter if it's minus or positive. Negative here really just signifies that we're on the left-hand side of the lens. Now you'll notice here that if we compare our object to our image, then we can notice a few things. Firstly, this image is real, okay? Why is it real? Well, it's real because the rays are meeting each other. Those rays are becoming concentrated at a particular point, and they are therefore forming a real image. The image is inverted. Well, why? Well, because it's upside down. You can see the top on the left-hand side maps directly with the bottom on the right-hand side, so therefore this is an inverted image. And it's also diminished. And again, we can check that here. If we look at the heights of these things, my object has a height of 2. The height of the image, hi, has a height of minus 1.33. Again, no worries about the minus sign here. This is just really showing that it's going down. And so therefore, we have a smaller image than the object. And this is exactly what you see when you're looking at most things, is that things look smaller than they really are. If I see a tall building in the background, I know that the image that I see of it is smaller. And what's maybe a little bit confusing is why it's not upside down in our mind's eye. Well, this is because our brain has learned to flip the inverted images just due to experience. So it's quite a clever bit of kit, all right. We notice it doesn't matter what the size of my object is, it's always diminished, it's always real, and it's always inverted. So for any distance greater than 2f, we have those same characteristics. However, as I approach 2f, which is about now, we notice something interesting happening. Again, we have a real image because the rays meet. We have an inverted image, but in this time, the image is neither diminished nor enlarged. You notice that my height on the left-hand side of the object is 2, and on the box, on the right-hand side, the image is also 2. So therefore, we produce an image which is the same size as the object. And that's a unique case where the distance, x as I've called it, or as in the simulation is d, is equal to twice the focal length. After this, we get interesting stuff happening. We notice we got a little bit inside the second focal length. So I'll tell you what, we'll go to maybe -6. Okay, in this case, I'm having to just zoom out a little bit. Actually, you can't see my image. I'll tell you what, I'll move it back a little bit. There you go. Okay, you can see here now. Again, if we go between just less than our 2f, then we got again a real image. A bit boring, really. Inverted again, it's upside down. But the interesting bit is now actually this thing is getting bigger. Our image is getting bigger. You can see an image of 2.47 in this case. Compared, I think that's because I've slightly modified the height, yeah, compared to our height, which has changed to 1.87. Okay, so in this case, we're producing an image which is real, inverted, but enlarged. In other words, it is bigger. And again, this behavior will continue until we hit that point inside that first focal length. So I'm just going to sort of move this through. Just believe me here that even though you can't see it now, you're getting some quite tricky stuff here. Let's go right inside that focal length. Okay, at the focal length we get no image. However, when we then go inside, we start to see something a bit weird. I'm just gonna bring this guy right into here, say for example. At a distance less than the focal length, in this case 2, you can see that my rays diverge. They do not meet. Okay, but what we're able to do if our eye was down in the bottom right hand corner, then what it would do is it would extrapolate back those rays so that it would appear that they come from this point behind the object. And when this happens, this is called a virtual image. The rays have not met each other. The image would not form on a screen. However, we are able to form it in our eye because our eye has a converging lens in there as well, and it's able to help form that image. You can see here, obviously, that the image is upright because the top of the image maps to the top of the object. And once more, we're definitely enlarged because if you compare the size of that image there, it's twice the size of my object. The reason that I've wanted to map these out is because there's a lot of different things going on here. There's a lot of confusing stuff going on here, and I know that students have a lot of trouble processing, for example, the different cases here. These are the 4 cases that you're expected to have an understanding of. I should say at this point, the last case of these, this x less than f, is one of the most popular ones with examiners. They really like setting it because they understand that this idea of virtual image is a really tricky one for students to deal with. So please do take some time to become comfortable with the ideas of virtual images because I'm fairly certain you'll be answering an exam question about them some point soon. All right, I hope that's clear, and thanks very much for watching. If you've got any questions, please let me know.